Now? Okay, sure. So hello, dear audience. Hello, everyone. Welcome warmly to this presentation. About providing information that I put in this seminar, I hope I try to make a, compromise between the different level, the bachelor students, master students, PhD, and of course, professors. About this seminar, just as a general information for you to attract your attention in control, and maybe you can use in your own works. About introducing myself, you can call me Hosein. My name is Hosein. Originally, I'm from Iran, and I did my bachelor and master in Iran. Again, second master and PhD in China, in Joint Institutes, SJTU with Michigan University. And then I went to UFRJ for first postdoc and second postdoc with Professor Antenor and Professor Juan in the project of microgrid. We are going to design novel controllers and novel control for microgrids. About the expertise that I had experience and I have is intelligent control, that my background in control, about fuzzy, narrow fuzzy, and neural networks. So nonlinear control, of course, some classical smart garage automation, robotic control, electromechanical system, and chaotic control. So today, I'm going to first introduce fuzzy, adaptive fuzzy, and second, introduce some nonlinear control that maybe by using the classical controller, designing the controller for them difficult. So how fuzzy can be trustable in industrial projects. This is my target today. So this is the biography that I explained. About the work that I did and professor that I was in international, I was in contact. First was Professor James Lamb. He was my co-advisor. He is the well-known professor entire the world. He was in Cambridge first, now he's working in China. Second, Professor Dr. Wei Zhang, he was my main supervisor in China, and also he's well-known professor in the term of control in Germany and China. And I have written 2 books with Professor Oscar Castillo. He's in Mexico, and he's the professor in the term of fuzzy. He was very close friend with Professor Lotfizadeh at that time. So Professor Lotfizadeh passed away, unfortunately, and he is one of the people that continuing his works. The research center that I worked first was the Research Center of Automation in Shanghai, that we worked different controller by perspective of having chaotic behavior of the system, because many industrial systems act chaotically. And so designing the controller for chaos system is tough, difficult. And second was the BYD company. BYD company that produced car, making a car. We designed a novel intelligent control for induction machine. It was my background and international cooperation. So let's get started from introduce Professor Lotfizadeh. You know him very well. Originally, he is from my country. He's from Iran, and he immigrated to United States. When he introduced fuzzy that time in 1965, actually that time, because fuzzy had a novel perspective, have a novel knowledge in the term of mathematics, no one paid attention to him, and he was innocent that time, if I want to say honestly. And it was not fair because he introduced a novel knowledge and it was silent for 20 years, until in Japan, some researchers designed a controller, fuzzy controller for the metro underground in Sendai city. And so metro is the sensitive project because it's working with human, directly human get into the metro, and then so because researchers say Zadeh introduce a new knowledge that doesn't have the classical mathematics background, so we cannot trust him. After Japanese design this industrial project, it's become more trustable for industry. So it was the first revolution of fuzzy. If I want to say simply, what is fuzzy? I can say today is hot. So you understand me. Did I work with mathematics? No. If I say Brazil is a hot country, you understand what am I saying, but I didn't work with numbers. Or you say in Brazil or in every country, people are tall, people are short. So we didn't talk with mathematics, but you understand what am I saying. The principle of fuzzy is become from the human knowledge. So human knowledge can introduce fuzzy, is the background of fuzzy. By some membership function, if you look at this membership function, the percentage of being hot is introduced here. For example, if we categorize the city of Brazil, Rio de Janeiro, São Paulo, south of Brazil, we can introduce them by this membership function, how much percent they are hot. For example, Rio de Janeiro by 100% is hot, but São Paulo with 90%. So this is the human knowledge that we didn't talk with mathematics, but it's understandable. So this is the first introduction of fuzzy. Of course, if you want to, looking for reference, you have a professor here, Professor Fernando. He worked with the fuzzy. I saw he have written a fuzzy books, so you can study about it. And also Professor Wang, he's Chinese. He was the first person that started working with fuzzy. Of course, nowadays fuzzy developed. Fuzzy go to fuzzy type 2, fuzzy type 3, and they work in training algorithm. But this is the first background. If you don't have this background, what is fuzzy? So you cannot go ahead. If we want to have the simple introduction of fuzzy system and why we are going to use the adaptive fuzzy, because it's very important, why we left fuzzy, why we don't use fuzzy directly, and why we switch on adaptive fuzzy. What's the reason? So if you look at the history of fuzzy, in 1990, successful application of fuzzy logic increased in automated control. So this is the first period that revolution happens in intelligent controllers. Because before that time, all the controllers was classic control, like a sliding mode, like backstepping, like PI and PID, still PI and PID working in industry. They have a lot of problem and people support them. But if we go through the details, if we consider some nonlinear things, so we can say making the system linear and try to design a controller nowadays is not useful because there are a lot of nonlinear terms in your loop that you ignore them if you want to design a linear system. So it's not fair. Some researcher just defends PI and PID because it's easy to design and it's cheap for implementing. But you ignore many things that after designing controller, these things, the nonlinear terms that you ignore can make a problem for you. That's why we are switching to nonlinear. From 1919, especially that time, the devices, industrial equipment become complicated in the term of mathematics. If you look at the model, the new devices, the model are highly complicated. So that's why we are looking for adaptive. So first I introduce again history of fuzzy. So as I mentioned, many processes, many projects attract the attention of fuzzy, make the fuzzy trustable because it was done in real project in industry. And the problem in fuzzy, because it doesn't have the background, mathematics background, so we cannot sometimes prove stability if you use the pure fuzzy. Because sometimes if we define the pure fuzzy, you need to manually design the membership function because the training this membership function is important. So this is the problem of fuzzy, that you cannot prove stability if you use the pure fuzzy. So that's why we mix it with adaptive to become adaptive fuzzy control. Of course, fuzzy has other applications like classification. We can classify different things. We can design observer, we can design controller, we can design estimator, and each one has its own application. But the main reason that we in controller or in observer, we switch from fuzzy to adaptive fuzzy is this, to prove the stability. Because when you design your controller, you need to prove closed loop system is stable. And we have a different type of stability, not just one type. So this is a reason that first I introduced the adaptive control. So you know adaptive control after World War II. Maybe that time during World War, adaptive control because silence, it became silent by researchers because of politics, I don't know. But after that, it's tried to develop fast. I mean, many papers come from Russia, come from America, different country, Brazil. So they try to develop the adaptive control fast, especially in 1990. And we mix fuzzy control with adaptive control, and we call it adaptive fuzzy to have the properties of fuzzy to solve the complicated systems that we cannot control them by classical method, and also use the stability that come from adaptive, mix them together, and we call it adaptive fuzzy. So this is the main properties of adaptive fuzzy controller. We can design a new controller for complicated systems, and we can prove their stability. So according to the explanation for training the membership function of the fuzzy that I discussed, we have many type of ways. We can use some neural networks. We can use Kalman filter. We can use different ways. We can use genetic algorithm to train these membership functions based on our system. As you know, Wang defined it. Wang was the first person that have written a book about fuzzy control. We say adaptive fuzzy system got a training algorithm whose parameters and structure would be regulated through numerical information. By some information from system that you have, you can train the fuzzy system, and after that, you can prove its stability. So we call it adaptive fuzzy control. So what is the properties of adaptive fuzzy control? First, if you look, adaptive fuzzy are good nonlinear general estimators. As I mentioned, many nonlinear systems, you cannot, or it's very difficult to use classical control. For example, in the next slide, I will show you chaotic systems. Chaotic systems are very complicated systems. If you really want to define, for example, by a sliding mode, it's impossible or difficult. Or you have a lot of problems like chattering and many things. Backstepping, when you go to the steps, it's very difficult. PI, impossible, never, cannot undo. So this is a very good nonlinear general estimator. Fuzzy control is easy to implement. This is another important part of fuzzy, that we can implement fuzzy controller. Because if you some other nonlinear controller, when you design, implementation is impossible or is very expensive. For example, why is still PI and PID working in some project? Because they are cheap. When you want to implement controller, it's cheap and it's easy. But why we don't switch practically from PI to a sliding mode? Why we don't switch from PI to feedback linearization? Because it's expensive if you want to implement. There is an IC, sensitive IC, that this IC can have this complicated equation, designed for this complicated equation. It's too expensive. So that's why researchers prefer, especially in industry, that economic is very important. People still work with PI and PID. But fuzzy has this talent to be implemented by developing VLSI ICs, especially Germany nowadays working in project to change from PI and PID to fuzzy control. There's cooperation, I think, in Hannover University between two departments, electronic and control and power electronic, to have all this together. So another important part of fuzzy control is adaptive fuzzy control does not depend on model of the system. When you are going to design the controller, your controller is not dependent on model, no matter what is the model, how much is complicated. It's very important. And then adaptive control can guarantee the stability and robustness. So when you design the controller, your controller is robust, totally robust, so it can be trusted. So this is the defense of fuzzy. Why adaptive fuzzy control? If someone asks you, this is the reasons that we are going to switch from classical controller to intelligent control. And nowadays is a hot topic in the world. If I want to classify adaptive fuzzy control, you can classify it in two parts, direct and indirect. What is the difference between them? Direct, you directly design the controller. For example, a sliding mode adaptive fuzzy controller. Directly you design by some algorithm, by some method. It has its own problem. But indirect, what is the indirect adaptive fuzzy controller? First, you estimate the dynamic of the system. You don't know dynamic, or you know dynamic. First, you estimate it, then give it to another controller. So controller design can be designed by the dynamic that you estimated by fuzzy. We call it adaptive fuzzy controller. Most of my work is categorized in this part. I work with indirect adaptive fuzzy controller because improving stability, sometimes finding the Lyapunov function is difficult when you're going to direct adaptive fuzzy control and other issues that it has. So if you see in the paper direct and indirect, what is the difference between them? Directly you use some algorithm and method. But indirect, first you estimate the model, then give it to another controller. The controller can be every controller because you have the exact model of the system. The properties of this controller compared to classical, you have the exact model of the system. Because having the exact model sometimes is impossible. For example, airplane is moving, missile when go to the space. So the model is difficult to estimate because, for example, missile go to the space, mass is changing, right? But do you have the sensor to measure the mass? It's very expensive or impossible. So when you design the controller based on the first dynamic and missile went into the space, so all your calculation become wrong. Sometimes in some paper, you can see we mixed some other controller with fuzzy. I put this aside for you, especially for students, to say something to you. Maybe it's useful for you. When we are going to design the controller, first we need to see what is the properties of the controller, what problem you're going to solve. Some people just change the controller. For example, when I ask them, why did you, for example, change backstepping with feedback linearization? For example, in converters that you know, DC-DC converters, you're going to design controller. Other researchers work with backstepping. Okay. I see this researcher work with feedback linearization. When I ask the reason, so when you design a new controller, you need to solve any problem. Otherwise, other controller done. So we don't, in engineering, we don't want to make things complicated because we want to have implementation. We need to make them simple, right? So you need to know every controller has what properties. What is the properties of this controller? What's the properties of this controller, and what problem you're going to solve. If you switch from backstepping to feedback linearization, you need to have a reason for that, or you need to have a background for that, not just changing. Of course, if you change, you will get the result. Even if the result is same or similar, it can be accepted in journal. Not high-level journal, but medium journal, because reviewer look at your works. Okay, it's another new controller, but you didn't do any novelty in your work, right? So this is very important. You know the properties of every controller. So the people that want to work with control in power electronic control, in robotic control, in any system, first, you need to find your problem. What problem I want to solve? Tracking, stability, speed, error, what? Then, which controller is good for this problem? Then you can mix it. For example, you can see, I don't know, you're familiar with sliding mode or not. Sliding mode, of course, control. A sliding mode has a chattering. It's connect and disconnect. It's a robust controller, attract the state of system into the slide, into the line. When the state of system came to this line, they cannot change, they become robust, okay? But in this line, we have chattering, connect and disconnect. What are state of systems? State of systems, for example, can be important things for you. For example, can be a parameter in converter that makes switching, okay? But this switching by this frequency can be damage for your system. For example, a sliding mode. I design a sliding mode controller for converter. The first comment that you can put is chattering. You have chattering in your system. If you want to implement it practically, you have a lot of problems. After a while, the system will be damaged, or robotic too. For example, you have arm of robot is very sensitive. The robot, especially that work in hospital, that do surgery. We have robots, for example, in China, that they do surgery instead of doctor, or in Japan too. So if you design a controller that have chattering, so the person that can be died because it's have chattering, try to connect and disconnect. So it's very important to know controller, not just look at the name. So here I put something for you. For example, we have the fuzzy control with sliding mode, because sliding mode is very good. Sliding mode controller can be mixed with fuzzy control to estimation error. Sometimes we have in estimation, we have error. So a sliding mode can help us to tolerate, okay, to undo. Another controller can be used in adaptive output feedback control. These are just examples to give you the overview. Of course, anyone can need to read their own paper, you know, to become a specialist in one. For example, in control, the person that is PhD or master, just working in this part. You don't need to know all of them. If you want to really become a specialist, you know, get focused in one part. So I put some example for you. For example, HNFT, that they were working on that. Why some people use in converters? Why? Because it has to minimize the effect of external distributions. Can be minimized, and you have a lot in your converters. Okay, so know the system very well, know the properties of the system very well, know the controller very well, then design the controller for them. Then choose the correct controller. This is the way that you, at least I do my research. This is another example, so I jump fast. Another overview that I want to give you as a control designer is every system has a specific dynamic model. If you look at here, we have affine, non-affine, and, for example, nonlinear feedback system. Each one has their own properties. For example, maybe a sliding one doesn't work for this kind of dynamic. You can simulate, you can compare your dynamic with each dynamic that you can see here. And each dynamic has its own properties. Okay? Some controller maybe doesn't work for some specific dynamic. So it's very important to know the dynamic of the model too. So after finishing this seminar, if you work in every system, you can go to papers. You can see the researcher that did research. Definitely he defined the mathematical model of the system. You can compare in which category it can put. And then go to the controller that you're going to design. See, the controller can be suitable for each dynamic. Okay, so this is another perspective of the controller that we need to know. Another type of fuzzy system is type 2 fuzzy system. That type 2 fuzzy system is the new fuzzy system. I work with fuzzy type 2. What is the difference between fuzzy type 2? Just I jump from this PPT quickly because maybe it's not your expertise, and just I want to give you the overview. The first reason that we jump from fuzzy type 1 to fuzzy type 2 is fuzzy type 2 has more capability, is more strong to estimate the dynamic of the system, is more stronger. So that's why we are using fuzzy type 2 systems and switch from fuzzy type 1 to fuzzy type 2. If you read the old books, they just get focused in fuzzy type 1. But fuzzy type 1 is finished, it's done. And they are going to fuzzy type 2. And after fuzzy type 2, I work with fuzzy type 3. We improve the fuzzy. Why? Because systems become more complicated. Okay? So if you want to start working with fuzzy, you need to start with fuzzy type 1, then get switched to fuzzy type 2. And what is the properties, what is the, benefit of fuzzy type 1, fuzzy type 2 compared to fuzzy type 1? Just capability to estimate the uncertainties. What are uncertainties? What is uncertainty? You know? Who can give me the explanation about uncertainty? For example, in converters, student. The example in converters or in, for example, any system in robotic, what is uncertainty? Noise. It can be noise. Noise is kind of uncertainty, but it's categorized in noise, in distributions. Uncertainties are parameters that change during working. For example, induction machine, when it starts working, some parameters change, like resistance of the rotor, right? Because of the skin effect. Rotor has a skin effect. The resistance starts to changing during the work. So if you design the controller based on fixed resistance, when induction motor start working, especially it has overload or it has load or sometimes load, the shaft become without load, no load. So the resistant rotor is changing. So changing some parameter. If you look at the dynamic, resistant rotor play an important role for you. And you need to consider it in your dynamic, in your designing. So we call it uncertainty. But some uncertainties that they are famous. in designing controller, I put them here, that they are novel uncertainty. First, uncertainty in inputs due to noise and condition of observers and sensors. Nowadays, sensor play a key point in your projects. You have a lot of sensors, right? You cannot ignore them nowadays. All the developed sensors has highly nonlinear dynamic, and they change because sensor company, they don't care. So what is the dynamic? Just they want to design a sensor that have accuracy for you. So, but when you put the sensor in the loop, because you have a loop, right? You have a closed loop. This sensor has a nonlinear dynamic, highly, and can create noise for you too. Even its cable, coaxial cable or different type of cable that you have. So uncertainties is coming from noise and observers. One of the way that we have uncertainty in the system can change the parameters. Second, uncertainty due to condition of operation of the controller. Sometimes the controller can need to be switched, right? So this switching can make uncertainties, can change some parameters for you that you design. Uncertainties from noise data. When you want to design the fuzzy controller, sometimes we give noise data to the controller to train the fuzzy, to train this membership function. So this noise, this kind of noise, kind of uncertainties, you need to consider. You cannot ignore. And another uncertainties that I explained, like a skin effect of induction motor, can changing the variables. When you have the system during the work condition, some parameters start changing from the real value. We call them uncertainties. What is the meaning of adaptive? Adaptive, we estimate these uncertainties online at each moment. Each moment we need this value to give to controller. So this is the work of adaptive. So this is this slide, I jump quickly. This is the feature of fuzzy type 2. As you can see here, the membership function is different from the first membership function that I introduced you. This membership function also has fuzzy. So as I mentioned, in fuzzy type 2, we have the, better capability to design the complicated systems. This is the general perspective of a fuzzy at the beginning. So you have the crisp. This crisp is numbers. So you make them fuzzy, by membership function. Then you implement some rules on the fuzzy based on your designing. When you implement some rules on the fuzzy, then you need to again make them as a numbers. All of these steps need designing is just give you the general perspective. And after that, your controller is ready or can act as every application that you consider for fuzzy. So the example, I want to give you the first example that I work in BYD company's induction motor. I want to show you how I designed the adaptive controller for induction motor. I pass the slides quickly because of the lack of the time, and I don't want this presentation to become boring for you because maybe you're not too much a specialist in the term of control. I want to show you the example and give you the overview. So induction machine, as you know, has a lot of application in industry, especially nowadays in vehicles. In vehicles, BYD, they use the induction motor because of its properties. It can be trustable motor, it can be, can endure during the different kind of working conditions. So it's a trustable machine for us. So in industry, it's kind of the very important machine, but the problem that we found in induction motor is, let me show you the challenges that we found first. First challenge that I found, most of the previous works depends on accuracy of mathematical model of the system. When you look at the mathematical model, most of the paper refer to some other papers. But originally, when this mathematical model came out, maybe some identification or come from some other researchers. But all the time is not exact. It doesn't have accuracy because it's impossible. It's describe your system. When you have the mathematical model of the system, just describe your system. It doesn't have accuracy. And when you design controller by classical controller, it's because you design the classical controller exactly based on the mathematical model. So if the mathematical model is not accurate, so all your design is wrong. Become wrong. Of course, it can act similar, but become wrong after a while, right? So this is the first challenge. Second challenge, finding some, disturbances, some noise, some faults, especially. Another key issues that I want to mention in this seminar is many researchers, when you design controller, you don't consider the faulty work of the system. Just to consider in normal work. Of course, in normal work, the key can control the induction motor too. By the contactor, by simple key, you can control it because nothing happens. It's normal work. You need to consider faulty condition. When you have noise, when you have uncertainty, when you have disturbances, you need to look in which part I have all this together. So it's very important. So the challenge is to be found. Another system that I work, as I mentioned, was the chaotic systems. What is chaotic system? Maybe you first quickly I introduce chaos system. Chaos system is kind of the system in mathematics perspective. If you look at the chaos system by the mathematics overview, is highly nonlinear, totally nonlinear. Is the maybe we can say the first nonlinear system is chaos system. All the industrial systems work and act chaotically. They can have a chaotic behavior, especially converters. Okay, power electronic devices, they act chaotically. Why we don't find many paper from internet or other, because it's difficult to design a control. And some people leave it. They go through the relay protection other way to control the chaos behavior. So it's very important we consider the chaotic system. Many systems act chaotically. So it's highly nonlinear, depends, is sensitive or depends on initial condition of the system. So it's very important mathematically. When you start the system, when you start working, it depends on this. And they have an unpredictable behavior. You cannot even guess what is the behavior. So it's very difficult to design the classical way for control. I put many different systems here. Of course, converters, communication, mechanical system, economic. For example, if voice recognition and telecommunication. For example, in economic, if I want to give you the example in chaos system is COVID-19. COVID-19 is kind of the chaos system for economy. Make the economy chaotic. Can you predict what will be the economic of the world in 6 months when we have COVID? No. What's going on? No. No one can do it. But I saw in Michigan, United States, they try to design economic systems based on COVID. They put the COVID dynamic into the economic system of USA, and they try to design the controller for economic, because economic is one of the important parts in control. How we can control economic? By this chaotic behavior. Okay, so if you look at the chaos background, chaos is old because many people work old. But it's important. Nowadays, we consider our industrial system when they act chaotic. The chaotic behavior of the system is very important. That sometimes is ignored. So these are the important type of chaotic system novel, Lawrence Chen. This researcher was some researcher that they try to simulate some, at least they can show, they could show some mathematical model of some chaotic systems. And the challenges I explained to you: complicated dynamic, unpredictable behavior, and sensitive to initial condition. The first work for induction motor was I&I controller that I did in BYD company. I just want to show you the novelty that we consider in this work and give you the perspective. We consider two faults of induction machine. First, change in rotor resistance, because rotor resistance starts changing during the work. And second, change in load torque. We have a different type of variable torque. Okay, suddenly overload come to shaft, suddenly take out. So we consider these two as a challenge. what is the novelty of this work? We consider as theta 1 and theta 2 in dynamic of induction machine. If you look at the dynamic of, the mathematical dynamic that I was explaining is this. The dynamic of IM. I told you, it should be accurate if you want to design classical control, but sometimes it's not. If you look at different paper consider different type of dynamic of induction machine. Which one has more accuracy? We don't know. Because they use the different type of identification. So here we try to consider theta 1 and theta 2 inside the dynamic. When we put them inside the dynamic, so they become adaptive controller, estimate them online, time by time. So controller become robust and adaptive together. Of course, these are the steps that we took. I don't want to get focused, just I want to show you the results. This is the overview perspective. Here is the proposed controller. And this is the properties of induction motor, as you can see. And this is the variation trajectory of load torque. Load can start variation. Suddenly here we have the overload. And of course, the overload by variation. And this is our result. You can see the reference and tracking. So during fault and normal work of induction motor. By these two faults, motor induced to working. Trajectory of rotor speed and trajectory of rotor flux. Both of them work. Smooth and without any fluctuation. Another important part of the control that you need to get focused when you design controller is control signals. If you design the controller and control signal is not smooth, you cannot implement it, and it's very expensive for implementation. So having the smooth control signal is another thing that you need to pay attention. For example, I saw a paper that it's a personal experience to share with you, that they designed controller for I think it was for robotic, but the control signal has a lot of fluctuation and it was not acceptable. If you ask some person that is a specialist in mechanical engineering and mechatronics, say this control signal can be accepted for your system, she or he say no, not at all. Because this controller cannot be implemented. You design controller works. But this control signal is very important. So when you want to get result, you need to pay attention to your control signal. What is control signal? Producing signal, give to actuator. It's very important. So this is the results that we consider. This is the faulty condition of machine. As you can see, still the signal are smooth. We don't have any fluctuation. Just I go past to show you. Control signal are smooth. There is no specific fluctuation just here, but controller can endure because nowadays they are implementing this controller in BYD company, and this is the comparison with other works. This is another thing that I want to get focused, and unfortunately, some people don't pay attention to this. When you, as I explained at the beginning, when you design your controller and you design every observer, controller, estimator, you need to be able to compare your work with other works. Some people don't have it in their thesis, in their paper, and in their work. How you want to show you have novelty? How you want to prove it? You have novelty. Some researchers say, oh, I have the similar controller, simple controller, by better result. So you cannot defend yourself. It's very important to put comparison in your work. As you can see here, we put comparison with different type of controller by RMSC. What is RMSC? The error. The error in tracking. We calculate the error of tracking and we put with different type of control. And you can see the error in my controller is much less than other controllers. So this paper, that time excellent. It's very important you compare your work. Another work that we did with induction machine is the same condition, but in this work, we didn't consider we have dynamic of the system. In this work, we don't have any information about this dynamic. We consider is like a black block. You don't know what's inside and what is changing. How we design this controller? By using the fuzzy perspective, employing fuzzy type 2. As you can see here, we have fuzzy. And we train this fuzzy by neural networks, the membership of this fuzzy. and the controller design. And we prove their stability. First, I design the fuzzy controller, estimate the dynamic, then I give it to the controller. I will show you. Look here. First, we design the fuzzy. Here is the system. We use the fuzzy. We estimate the dynamic of the system. Then we give to controller. Indirect fuzzy system. Here is your system. Okay. First, estimate the dynamic of the system because I don't have any knowledge about dynamic. Then I give this estimated to the controller. And let's see the result. This is indirect fuzzy type 2. So prove their stability. As I told you, adaptive fuzzy, we need to mix with some mathematics here by choosing this Lyapunov function. We prove their stability, and result is, you can see the result. Is the output trajectory of rotor speed. Tracking happens, and tracking error is nothing. We don't have any tracking error. And here, again, in faulty condition. Control signal are smooth. Just a few overshoot we have here, that is nothing compared to implementation. Other works. And in faulty condition, also we have the good results. So this is the comparison, as I mentioned before, and also with other fuzzy type. Comparison between fuzzy, different controller, and different system. You can do both of them in your works. For example, you have a DC converter, okay, you design a new controller for that. You need to compare this controller with previous works, or you need to change your system. Controller to controller or controller to system. It's very important to have in your work. So I'm going to finish my presentation now because just it was my point, my target in this seminar was give you a overview and good perspective about control. I hope in the next presentation and seminar, we are going to go to more details, and I will present for you the chaotic controller. So what is chaotic system, and how we can consider some industrial systems as chaotic systems, and we design controller for them. Okay. I hope this seminar today be useful for you and you enjoy. And if you have any question, now you can ask, or you can send me an email. Thank you very much for your attention. Thank you. Thank you very much. Any question?
Give you that.
You can ask me your question, please, and feel free to ask this type of question to discuss scientific discussion. I'm here to help if I know something.
How was the accuracy of the identification of the one? How you guys were doing the identification? Because identification is the key point of your adaptive fuzzy type. How you guys were doing that?
Actually, in that second work, we didn't consider we have the dynamic of the system, right? We consider it's unknown. We don't have any information. But in first work, so we trust other researchers that they did. I mean, there was another paper because just as the research, you know. And as I mentioned, if really you want to find the exact dynamic of every system, it's just difficult. Because just the mathematical model can describe your system similarly, not exactly. Accuracy is important. So in the first one, just we we took from other researchers. The researchers done, okay, so trustable, so we consider that they're dynamic. But in control, we have this knowledge, we have identification systems by filter Kalman, by, I don't know, standard filter Kalman, some estimators, even fuzzy, and some classical way, you can find the dynamic of every system. Of course, it's kind of knowledge in control, we call it identification. Any other questions?
Thank you.
Question?
How do you think in smart grid? with many power converters, each one with control, classical control. And we want to design a fuzzy controller for stability of the microgrid. How we can mix this kind of classical control device and the fuzzy control, and how what do you control?
Exactly. Just well, so nowadays we have a new perspective of fuzzy that become fuzzy type 3. Fuzzy type 3, because of the membership function, is different with fuzzy type 1 and fuzzy type 2, so has more capability to induce uncertainties. So the question that you ask depends on what we're going to do. For example, if we are going to control the frequency, it's another strategy on voltage stability. But generally, the things that I can tell you, we can hire the proposal that I have written and sent. We can hire fuzzy type 3 indirect adaptive controller to design this kind of request. I mean, we can consider in the new work complicated dynamic of the system and prove their stability. Because if we, for example, sometimes we cannot remove the local controller. So we have some local controllers. Okay, so local controllers is just designed for some specific. But considering all the system, so we can hire the indirect fuzzy adaptive control, and so we can prove the stability. But again, it depends on the problems that we are looking for. For example, frequency stability, voltage stability, or reactive and active power adjusting. So what we are going to do. We can consider all these issues, but step by step. So we cannot consider all of them together, because every controller when we design, they focus on one subject. Complicated.
But if you have many agents in the system,
so multi-agent is another right. Multi-agent, we can use the multi-agent knowledge, because control has multi-agent, and by multi-agent perspective, mixing with fuzzy, of course, especially if you have a master slave. Because I finished the seminar, but in the following PPTs, I have this design by fuzzy type 2 that we have a master slave system, the system that is a slave, and master try to switch it, try to follow. So this is another knowledge and control that we can hire for you. But how we can do it, so it depends on the design that we are going to do. But we have the solution for them, definitely. Because in classical way, that's, of course, I cannot say classical way are bad, because of course we have this kind of professors and researchers that they focus on classical. And they defend classical because it has a more background, it's a much mathematical background. But here for us to reach reasonable results for our project, of course, multi-agent is one of the solutions for the all agents and hiring the fuzzy type 3 nowadays. Because nowadays fuzzy type 3 is another important topic in the world to solve this kind of solution problems.
So, for example, following Professor question, is fuzzy able to work with multiple systems?
I'm sorry?
It's like fuzzy able to work with MIMO systems, like multiple inputs.
Of course. Of course, because SISO is the simple, is the simple, like, for example, induction motor is MIMO 2. But SISO systems are very simple systems in the term of control perspective. MIMO so is the importance. Of course, it's kind of like a converter is kind of a good example for MIMO, because you have a different input and different output. For example, like active and reactive frequency and everything that you consider in the control loop.
Because you just said, like, for example, we should think of controlling using only one subject. So like, oh, you want to control
One subject. I was not subject meaning just subject. For example, reactive power. For example, stability. I mean, the subject in control. Control signal. Focus. Of course, you can have all of them together. I mean, MI and
okay.
Of course, this is the one of the novelty of us for MIMO system SISO. Because SISO nowadays we don't have SISO system. SISO just come to box for examples.
Yes, one thing that you talked about in the beginning was that this idea of adaptive control that start from after the war, and I probably when I was doing my PhD degree was the time of disgrace of
Right.
adaptive control because you are okay with the identification part and you are okay with certain type of controls like parametric dependent controls. And the problem is that when you put together, then your code will work with the wrong parameters.
Exactly.
Because it was very dependent on the exact parameters.
Wow.
Then this has evolved in robust control, I think. And but the way you talk about fuzzy is like you have solved this problem because this problem has a problem of convergence and of course the stability of the system. So you divide of the class of fuzzy problems and you said that you focus in the second one where the identification is already is available, is products that you need are available, and then you focus on the first control. So have I got it right? So you can, using fuzzy, solve in general terms this problem of stability of adaptive control.
Exactly. So as I mentioned, because at the direct way that we're going to design the fuzzy, of course, also that way is not dependent on mathematical model, but it has its own issue because we directly design the fuzzy controller and put it on the open. But in indirect way, as you mentioned, we first estimate the dynamic by all changing everything that we have, the problem, noise, uncertainties. Then we have the adaptive online estimator. This fuzzy that we are using also is adaptive because online start. But what is the speed of this online? What is the, it depends on the algorithm that we train the fuzzy. So different algorithm, different fuzzy. Of course, this algorithm we need to prove stability too because it's sometimes going to the unstable. So after we have the dynamic, we give it to the controller, and controller can be simple because we solve all the problem in fuzzy. The controller can be kind of, for example, feedback minimization.
So, but you need a kind of not the rate of variations and things like that. You have to impose some condition or parameters can vary.
Can vary, of course. Parameter will vary because they're not under our control. But after fuzzy, so the variation are online, and the controller that we are using, the controller is robust too. But we know the value of changing value because as you know, in classical way, just they fix variation. They don't consider how much is varying give to the controller. But in this kind of design, all the time it's updated. The information that gives to controller is updated by time. So the accuracy is high, so it can do during any difficulty. Because the much more important thing in fuzzy is unknown value, as Professor mentioned. So we don't need to have this mathematical model of this complicated system. So this is one novelty of fuzzy. Another novelty, as you mentioned, is changing the parameters. Parameter changing, but so we estimate. So all the problem solving. But if I want to say the disadvantage of fuzzy, according to my experience, what is the disadvantage? Is of course some researcher work, but we don't have the specific structure. We choose the structure of the fuzzy based on some previous experience. So we say, okay, this structure works for robotics, so I will try to implement this structure of fuzzy only converters too, because robotics is much more difficult to control than compared to converter. Converter power electronic already compared to robotics is very simple. So this is the disadvantage of fuzzy. We don't know what kind of structure to choose. But nowadays, some researchers work to find this type of structure for a specific type of system. But about the issues that you mentioned, no, fuzzy can be used, but fuzzy can get good choice. No problem. Even implementation of the fuzzy controller is done now, especially Hannover University in Germany. They are trying to change because still they use PI. Especially. PI is harder, but PID because can't find the delay, so it's better. But they change it to fuzzy as they adapt it. Because I see.
There's another question I think the written will ask is, so you can see from the literature or what, from what you know, how to attack this problem of not in the machine level, but in the grid level. So you can use this to get stuff in.
Yes, exactly. Because one work I did in your RJ with Professor Alades was about this issue that Professor mentioned. We designed fuzzy type 2 for voltage stability, and we consider the huge complex of the system. Because, for example, if you read the Renewable Energy Journal or this kind of paper, just researchers consider one device. Say, okay, wind turbine and its control. But it's not micro. But if you consider all of them together in the micro and their variation, because PV has a variation, changing in producing, changing in parameter, wind turbine too, especially they use the specific induction motor as a generator in wind turbine. So if you, of course, we can consider all of them in micro. I can share the paper about this. Any question?
The one
Who worked with fuzzy? No one here worked with fuzzy type 1 or fuzzy. So what's your name?
Yeah,
Yeah. So what you work, can you please?
using linear matrix inequalities to control fuzzy systems.
So you apply this thing on any specific system? Or?
No, actually, my thing is more focused on linear matrix inequalities. Just the application instead of applying to uncertain systems, we apply to fuzzy systems.
So what kind of fuzzy you consider?
Type 1. Yeah, I think it's interesting to explore the possibility of type 2 now. I didn't hear about that before your presentation, so thank you for that.
Just because fuzzy type 2, if you, for example, especially when you work with uncertainties, the huge uncertainty you consider, of course, is much more stronger than fuzzy type 1. Fuzzy type 1 in many cases cannot do. Of course, has a good estimation, but compared to fuzzy type 2, no. So some points you consider in fuzzy type 1 that make, for example, especially in implementation, I see that I mentioned. If you bring all uncertainty on fuzzy type 1 because the membership function has one definition, so it cannot be implemented. Fuzzy type 2 and also fuzzy type 3.
I'll search the possibility of
Go
applying
ahead,
to
sure. And also we can train the membership function by fuzzy by machine learning. Sometimes for training, we can use the algorithm of machine learning. Machine learning can help us. Because about 20 years ago, some papers in Japan published, but no one pay attention because machine learning need a huge computer or super machine. But nowadays, by the computers, it can be done. It's much more acute than other methods. We call it machine learning fuzzy for training the membership function. Someone is interested. Research is very interesting. But we need some background in computer science too.
we can embed this controller in a common DSP.
For industrial project and laboratory by MATLAB and some interference, yes. But in industrial projects, You need to look for ICs. But we can order because Chinese do it. We can at least we can search for the way. Because I know the Professor Chen. He has a huge laboratory. He was our neighbor of my professor at that time, and he has a huge laboratory that works in this area. We can communicate with him what way we use to for the implementing of this control for industrial project. Because for industrial project, the Chinese looking for economical ways.
But it's specific for each application or
For
a general fuzzy control?
General. So, but again, depends. So if you have a general overview, it can be general. So if you want to be for each application, also can be our target.
It's a fully digital device or it's parts analogic, PGA or?
I think the IC can be digital. Thank you very much, dear friends, dear professors. I'm sorry if a little it was boring for you because it was not related to your direct major. But I tried to bring at least a new perspective for you, new good knowledge, good things that at least many people focus on them. Because sometimes when we discuss conferences and I attend, when we ask this type of, for example, the things that I put, there was the questions that different high-tech researchers asked from the person that present the work. For example, maybe it's interesting for you. In South Korea, the things that I told you, we need to have the comparison in your work. I was in South Korea in a conference with my professor at that time. There was a person, I think he was, I don't know which country, Vietnam or Japan, I forget. He presented his work. After presentation, one professor asked him a question. I have a simple question. How you want to prove this novel controller that you designed is better than others? He said, result is good. It's okay, result is good. But your work is too complicated. I have other method that if you compare this work to them, your work is not useful for the practical project. And he couldn't defend. So it's not so much pleasure in the conference. Just I wanted to share with you, care about these simple things, Maybe audience ask you, what is how you want to prove? You need to have some logical reason. For example, okay, my controller is complicated, but I solve tracking problems compared to other works. Tracking problem solved, so it's not. But when you have a similar result with more complicated design methods, you can put comments on your work. And you need to be able to defend it as a researcher. Thank you very much.
Obrigado.